help us understand what machine learning is, because that seems to be the key driver of so much of the excitement and also the concern around artificial intelligence. How does machine learning work?
So artificial intelligence and machine learning is about 60 years old and has not had a great day in its past until recently. And the reason is that today we have reached a scale of computing and data sets that was necessary to make machines smart. So here's how it works. If you program a computer today, say your phone, then you hire software engineers that write a very, very long kitchen recipe. Like, if the water is too hot, turn down the temperature. If it's too cold, turn up the temperature. The recipes are not just 10 lines long, they are millions of lines long. A modern cell phone has 12 million lines of code. A browser has 5 million lines of code. And each bug in this recipe can cause your computer to crash. That's why a software engineer makes so much money. The new thing now is that computers can find their own rules. So instead of an expert deciphering step by step a rule for every contingency, what you do now is you give the computer examples and have it infer its own rules. A really good example is AlphaGo, which recently was won by Google. Normally, in game playing, you would really write down all the rules. But in AlphaGo's case, the system looked over 1 million games and was able to infer its own rules and then beat the world's residing Go champion. That is exciting because it relieves the software engineer of the need of being super smart and pushes the burden towards the data. As I said, the inflection point where this has become really possible. Very embarrassing, my thesis was about machine learning. It was completely insignificant, don't read it, because it was 20 years ago. And back then the computers were as big as a cockroach brain. Now they are powerful enough to really emulate kind of specialized human thinking. And then the computers take advantage of the fact that they can look at much more data than people can. So I'd say AlphaGo looked over more than 1 million games. No human expert can ever study 1 million games. Google has looked on over 100 billion web pages. No person can ever study 100 billion web pages. So as a result, the computer can find rules that even people can't find.
So it's kind of, instead of looking ahead to if he does that, I will do that, it's more saying, here is what looks like a winning pattern. Here is what looks like a winning pattern.
I mean, think about how you raise children. You don't spend the first 18 years giving the kids a rule for every contingency and then set them free and then they have this big program. They stumble, they fall, they get up, they get slapped or spanked, and they have a positive experience, get a good grade in school, and they're figured out on their own. And that's happening with computers now, which makes computer programming so much easier all of a sudden. Now you don't have to even think anymore, you just give them lots of data.
And so this has been key to the spectacular improvement in power of self-driving cars. I think you gave me an example. Can you explain what's happening here?
This is a drive of a self-driving car that we happen to have at Udacity and recently made into a spin-out called Voyage, where we used this thing called deep learning to train a car to drive itself. And this is driving from Mountain View, California to San Francisco on El Camino Real on a rainy day with bicyclists and pedestrians and the 133 traffic lights. And the novel thing here is when many moons ago, I started the Google self-driving car team. And back in the day, I hired the world's best software engineers to find the world's best rules. This is just trained. We drive this road 20 times. We put all this data into the computer brain, and after a few hours of processing, it comes up with behavior that often surpasses human agility. So it's become really easy to program it. This is 100% autonomous, about 33 miles an hour and a half.
So explain, so on the big part of this program on the left, you're seeing basically what the computer sees as trucks and cars and those rocks overtaking it and so forth.
On the right side, you see the camera image, which is the main input here, and it's used to find lanes, other cars, traffic lights. The vehicle has a radar to do distance estimation, which is very commonly used in these kind of systems. On the left side, you see a laser diagram where you see obstacles like trees and so on depicted by the laser. But almost all the interesting work is happening on the camera image now. We're really shifting over from precision sensors like radars and lasers into kind of very cheap commoditized sensors. A camera costs less than $8.
And that green dot on the left thing, what is that? Is that anything meaningful?
This is a look-ahead point for your adaptive cruise control. So it helps us understand how to regulate velocity based on how far the car is in front of you.
And so you've also got an example, I think, of how the actual learning part takes place. Maybe we can see that. Talk about this.
This is an example where we posed a challenge to Udacity students that take what we call a self-driving car nanodegree. And we gave them this data set and said, hey, can you guys figure out how to steer this car? And if you look at the images, it's even for humans quite impossible to get the steering right. And we ran a competition and said, hey, it's a deep learning competition, AI competition. And we gave the students 48 hours, right? So if you're a software house like Google or Facebook, something like this costs you at least 6 months to work. So we figured 48 hours is great. And within 48 hours, we got about 100 submissions from students, and the top 4 got it perfectly right. It drives better than I could drive on this imagery using deep learning. And again, it's the same methodology. It's this magical thing. When you give enough data to a computer now and give enough time to combine the data, it finds its own rules.
And so that has led to development of powerful applications in all sorts of areas. You were talking to me the other day about cancer. Can I show this video?
Yeah, absolutely.
This is cool.
So this is kind of an insight into what's happening in a completely different domain. This is augmenting or competing, it's in the eye of the beholder, with people who are being paid $400,000 a year. Dermatologists, highly trained specialists. It takes more than a decade of training to be a good dermatologist. What you see here is the machine learning version of it. It's called a neural network. Neural networks is the technical term for these machine learning algorithms. They've been around since the 1980s. This one has been invented in 1988 by a Facebook fellow called Jan LeCun. And it propagates data stages through what you could think of as the human brain. It's not quite the same thing, but it emulates the same thing. It goes stage after stage. In the very first stage, it takes the visual input and extracts edges and rods and dots. And the next one become more complicated edges and shapes like little half moons. And eventually, it's able to build really complicated concepts. Andrew Ng has been able to show that it's able to find cat faces and dog faces in vast amounts of images. What my student team at Stanford has shown is that if you train it on 129,000 images of skin conditions, including melanoma and carcinomas, you can do as good a job as the best human dermatologists. And to convince ourselves that that's the case, we captured an independent data set that we presented to our network and to 25 board-certified Stanford-level dermatologists and compared those. And in most cases, we're either on par or above the performance classification accuracy of human dermatologists.
You were telling me an anecdote, I think, about this image right here. What happened here?
This was last Thursday, and that's a moving piece. So what we've shown before, and we published in Nature earlier this year, was this idea that we show dermatologist images and our computer program images, and we count how often they're right. But all these images are past images. They've all been biopsied to make sure we have the correct classification. This one wasn't. So this one was actually done at Stanford by one of our collaborators. And the story goes that our collaborator, who's a world-famous dermatologist, one of the 3 best apparently, looked at this mole and said, it's not skin cancer. And then he had a second moment where he said, let me just check with the app. So he took out his iPhone and ran our piece of software, our pocket dermatologist, so to speak, and the iPhone said cancer. It said melanoma. And then he was confused and decided, okay, maybe I trust the iPhone a little bit more than myself. And he sent it out into the lab to get it biopsied. And it came out as an aggressive melanoma. So I think this might be the first time that we actually found in the practice, using deep learning, an actual person whose melanoma would have gone unclassified had it not been for deep learning.
I mean, that's incredible. It feels like there'd be an instant demand for an app like this right now, although you might freak out a lot of people. Are you